Good morning, Om Swastiastu. Let me introduce myself. My name is Putra Hutabarat with student ID number 23055311075. I am from the Mechanical Engineering Study Program with Faculty of Engineering, Udayana University. At this video, I will explain about structure of metals and alloys. Chapter 2, Structure of Metals and Alloys. 2.1, Profile of the Atom. In his book, A New System of Chemical Philosophy, in 1808, John Dalton proposed the existence of small, indivisible particles that preserve their identities in any chemical reaction. Dalton further proposed that atoms were changeable with an atomic weight, and later developed the law of multiple proportions, which states that if two elements can form more than one compound together, then the ratios of the masses of the second element that combine with a fixed mass of the first element will be ratios of a small integer. PV equals nRT. The atomic concept also helped progress kinetic theory of matter and the laws of thermodynamics, or theoretical conversion between heat, energy and mechanical work. For example, in the kinetic theory of gases, the behavior of an ideal gas in a container of volume V at pressure P can be explained by PV equals nRT, where N is the number of atoms in the container, R is the universal ideal gas constant, and T is the temperature. This picture is Bohr atomic model of nitrogen atoms. Atoms consist of a positively charged nucleus and surrounded by negatively charged electrons in a path. Electrons can move from one path to another by absorbing or emitting energy, so that the energy of the atom's electrons will not decrease. If it moves to a high path, the electron will absorb energy. If it moves to a lower path, the electron will radiate energy. The positive of electrons at certain energy levels called electron cells. Atoms are composed of proton, neutron and electrons. Proton and neutrons make up the atomic nucleus, while electrons move around the atomic nucleus. Okay, next. 2.1, Bonding between atoms. Atoms interact with one another to form different states or passes of matter. The four fundamental states of matter are solid, liquid, gas, and plasma. Atoms are less tightly bound in liquids and gases than they are in solids, which result in a high degree of atomic mobility between atoms. Metallic bonding occurs when each of the atoms of the metal contributes its valence electrons to the formation of an electron cloud that surrounds the positively charged metal ions. Like this. Valence electrons are shared by all of the atoms. In this bond, the positively charged ions repel each other uniformly, so they arrange themselves into a regular pattern that is held together by the negatively charged electron cloud. Ionic bonding. Ionic bonding, also shown at this picture, is a result of electrical attraction between alternately placed positive and negative ions. In the ionic bond, the electrons are shared by an electropositive ion or cation and an electronegative ion or anion. The electropositive ion gives off its valence electrons, while the electronegative ion captures them to produce ions having full electron orbitals or suborbitals. As a consequence, there are no free electrons available to conduct electricity. 2.3 Crystal structures and defects. A substance freezes on cooling from the liquid state. It forms a solid that is either an amorphous or a crystalline structure. An amorphous structure is essentially a random structure. However, metals under normal freezing conditions normally form long-range, orderly crystalline structures. Except for glasses, almost all ceramic materials also form crystalline structures. Therefore, metals and ceramics are in general crystalline, while glasses and polymers are mostly amorphous. 2.3.1 Space lattices and crystal systems. A crystalline structure consists of atoms or molecules in a regular repeating three-dimensional pattern with long-range order. A distribution of points or atoms in three dimensions is said to form a space lattice if every point has identical surroundings, as shown at this picture. The intersections of the lines called lattice points represents location in space orientation. In space with the same kind of atom or group of atoms of identical composition, arrangement, and orientation. The geometry of a space lattice is completely specified by the lattice constant A, B, and C, and the interaxial angles alpha, beta, and gamma. Table 2.2 Characteristic of the 7 different crystal systems. This is crystal system, edge length, interaxial angle. Triclinic. A is not equal B is not equal C, and alpha is not equal beta is not equal gamma is not equal 19 degrees. Monoclinic. A is not equal B is not equal C, and alpha equals gamma equals 90 degrees, but is not equals beta. Orthorhombic. A is not equal B is not equal C, and alpha equals B equals gamma equals 90 degrees. Tetragonal. A equals B is not equal C. Alpha equals beta equals gamma equals 90 degrees. Hexagonal. A equals B but is not equal C. Alpha equals beta equals 90 degrees, and gamma equals 120 degrees. Rhombohedral. A equals B equals C, and alpha equals beta equals gamma is not equals 90 degrees. Cubic. A equals B equals C, and alpha equals B equals gamma equals 90 degrees. This is the picture of triclinic primitive, monoclinic primitive, triclinic base center, tetragonal primitive, tetragonal body center, hexagonal primitive, rhombohedral primitive, orthorhombic primitive, orthorhombic base center, orthorhombic body center, orthorhombic face center, cubic primitive, cubic body center, cubic face center. 2.3.2 Crystal imperfections and plastic deformation. Imperfections can be conveniently classified under four main divisions: point defects, line defects, planar defects, and volume defects. Point defects, also known as zero-dimensional defects, occur at any lattice node with a vacancy or missing atom, an extra interstitial atoms, or an impure atom. At this picture, this point A, B, and C. Line defects are known as dislocations and lie along an axis or line of atoms in a crystalline lattice. The main type of line defect is an edge dislocation, where a partial plane of extra atoms is present either above or below the dislocation line. Dislocation can be either positive or negative, depending on whether the extra tau of atom in the plane above or below the dislocation line. Where surface or planar defects occur. This is the picture of microstructure, this atomic arrangement. Whenever the crystalline structure of metal is discontinuous across a plane, surface defects extend in two directions over a relatively large surface with a thickness of only one or two lattice parameters. For example, grain boundaries are surface distributions between the crystal lattice of individual grains. At this picture, grain boundaries and pass boundaries are independent or of crystal structure. During mechanical twinning, atoms on each side of the twinning plane or habit plane form a mirror image with those on the other side of the plane. This picture shear stresses along the twin plane cause atoms to move a distance that is proportional to the distance from the twin plane. A comparison of the slip and twinning mechanism. The orientation, mirror image, deformation, stress. Orientation. In sleep, the orientation above and below the sleep plane is the same after sleep, while in twinning there is an orientation change across the twin plane. 2. Mirror image. Atoms in the twin portion of the lattice form a mirror image with the untwinned portion. No such relationship exists in sleep. Deformation. In sleep, the deformation is non-homogeneous because it is concentrated in bands, while the metal adjacent to the bands is largely under form and stress. In sleep, a lower stress is required to initiate it, while a higher stress is required to keep it propagating. In twinning, a high stress is required to initiate, but a very low stress is required for propagation. 2.4 Crystal structure of metals. This grain boundary sleep plane. Atoms within the grain boundaries are usually very highly strained and disordered, and so grain boundaries are high energy sites. Grain boundaries are also very thin, typically only 1 or 2 atoms thick. An example of this would be the precipitation of phosphorus along the grain boundaries of metallic stainless steel, the FCC system. This picture A, HCP, this FCC, this BCC, and this FCC again, and this BCC again. In close-packed structures, slip nearly always occurs along the planes of densest atomic packing, or close-packed planes. The FCC system has 4 slip planes, each with 3 available slip directions. The total number of slip systems, or a combination of a slip plane and a slip direction, is thus 12. The term close-packed is used because the atoms could not be arranged to fill the available space within the plane any more efficiently. At the point where 3 of the atom is this plane touch, the 3 spheres produce a small dip or seed, which is an ideal location for an atom to sit. If another plane of atoms is stacked on top of the first plane. Grains and grain boundaries. This reflects light and incident light, like this. Grains and grain boundaries make up the microscopic structure or microstructure of metal and alloys. Grain boundaries, as well as other microstructural features, are often observed by a process of specimen preparation known as metallurgy. Micrographs. The photographic image of a microstructure is recorded in a photograph called a photomicrograph or micrograph for short. Examples of micrographs allow carbon sheet steel with coarse, medium, and fine-sized grains are shown at this picture. 2.5 Diffusion. Atoms are very mobile in a gas or liquid, while the bonding of atoms in solids restricts their mobility. But atoms can move around in any substance, even solids. Atoms in a solid are constantly vibrating due to their thermal motion. Although it may be difficult to imagine, diffusion allows them to migrate to different locations within a crystal lattice. The vibrating atom may switch position with a neighbor atom in the lattice, or an atom may even move into neighboring vacancy sites or defect areas. Frankel mechanism. Vacancies can form by several mechanisms. In the Frankel mechanism, an atom is displaced from its normal lattice position into an interstitial site. However, this requires quite a bit of energy first. The energy to form a vacancy and then the energy to form an interstitial. 2.6 Solid solution. A solid solution is formed when two or more elements mix with each other in a crystalline lattice. Atoms of one element enter the lattice of a second element, forming a kind of partnership. The which is called the solid. The hot is called the solvent. There is only one solvent, but more than one solid may be involved. If not, most alloys of practical importance are solid solutions. For example, brass is a solid solution of copper and zinc. Copper pennies in the United States are 95% copper and 5% zinc. Nickels are 25% nickel and 75% copper. The key property of a solid solution is the solubilization of the solid in the solvent. There are in general four basic factors developed by Hume Rotary that influence the likelihood to metals to form substitutional solid solutions. Number one, relative size factors. If the size of the solid and solvent atoms differ by less than 15%, the metals are said to have a favorable size factor for solid solution formation. Each of the metals will be able to dissolve an appreciable amount of the other metal, on the order of 10% or more. Number 2, chemical affinity factor. The greater the chemical affinity of two metals, the more restricted is their solid solubility. When their chemical affinity is great, they tend to form compounds rather than a solid solution. Number 3, relative valency factor. If a solid atom has a different valence from that of the solvent metal, the number of electrons per atom, called the electron ratio E or A, will be changed by alloying. Number 4, lattice type factor. Only metals that have the same type of lattice structure can form a complete series of solid solutions. Interstitial solid solutions. Interstitial solid solutions are those in which the solid atoms are much smaller and fit within the space between the existing solvent atoms in the crystalline structure. However, the only solute atoms small enough to fit into the interstices of metal crystals are hydrogen, nitrogen, carbon, and boron. The other small diameter atoms, such as oxygen, tend to form compounds with metals rather than dissolve in them. Solubility limits. Like the solubility of salt in water, solid solutions also have solubility limits. Solid solubility is a measure of how much solute can be dissolved or incorporate into the host lattice phase diagrams. This temperature in Fahrenheit and this temperature in Celsius. This is line solvus line, solidus, liquidus, liquid plus alpha. Okay, the change in solubility limits with temperature are described in an essential term of metallurgy phase diagram. As previously noted, the phase of a solid refers to the structure of atoms in the solid. An alloy with a homogeneous common structure is a single phase alloy, although it is important to note that many alloys may also contain more than one phase. Illustration of the phase change of pure iron during heating or cooling. Below the melting point of 1540 degrees Celsius or 2800 degrees Fahrenheit, there are three temperature periods of when solid iron undergoes a phase change. Consider first the process of solidification as liquid iron cool to its melting point of 1540 degrees Celsius or 2800 degrees Fahrenheit. It begins to freeze with no further drop in temperature until it transforms itself completely into a solid form of iron referred to as delta iron or delta ferrite. Ferrite has a BCC crystal structure. Delta ferrite is the high temperature BCC phase of iron. After solidification of complete, the temperature drop at a uniform rate until the temperature of 1394 degrees Celsius or 2541 degrees Fahrenheit is reached. This temperature marks the beginning of a transformation of the BCC delta iron into an FCC crystal phase called austenite or gamma iron. The temperature stays constant until the transformation is complete. That is until all of the iron has an austenitic or FCC phase structure. Further cooling of the gamma FCC iron continues at a uniform rate until the temperature reaches 912 degrees Celsius. This is the transformation temperature when gamma iron begins the transformation into a non-magnetic form of iron with a BCC crystal lattice. The temperature holds steady during cooling until all the iron atoms are completely transformed into a BCC crystal lattice. This low temperature BCC phase of iron is referred to as alpha iron or alpha ferrite. 2.8 melting. Atoms are in constant motion. In liquids, atoms are further apart than in the corresponding solid. For example, the density of a plain carbon steel heated to the liquid stage is approximately 20% lower than the solid form of the same steel. 2.9 Solidification structure. Solidification of modern metal occurs by nucleation and growth process. During this process, atoms change their arrangement from the randomized short-range order of a liquid to the long-range order of a solid, or typically in the regular positions of a crystal lattice. In doing so, they give up much of their kinetic energy in the form of heat, which is called the latent heat of fusion. The resulting morphologies of solidification structure can be described on 4 different length scales. This macro, meso, micro, nano, and nano. Macro scale structure is a length scale on the order of 1 millimeter up to 1 meter. Elements of the macro scale includes shrinkage cavity, macro segregation, cracks, surface roughness or finish, and casting dimensions. Mesoscale structure is a length scale on the order of 10 to 4 meter. It allows description of the microstructural features at the grain level without resolving the intricacies of the grain structure. Microscale structure or microstructure is on the order of 10 until 6 to 10 until 5 meter. The term microstructure is the classic term used in metallurgy to describe features observed under the microscope. And the last, nanoscale or atomic scale. Structures are on the order of 10 until 9 meters or nanometers and describe the atomic morphology of the solid-liquid interface. 2.10 Using equilibrium phase diagrams. Phase diagrams are a fundamental tool that can be used to understand how solid solutions, crystal structures, and chemical compounds are affected by a temperature and pressure too, although pressure is typically not a major variable. For a given temperature and chemical composition, the phase diagram shows what phase or phases are present in the alloy under conditions of thermal equilibrium. Gibbs phase rule. Gibbs used the term phase for each homogeneous region of a system, and he expanded the concept to describe the thermodynamics of heterogeneous solids. The number of stable phases, or P, in a system is defined by the rule P equals C minus F plus 2, where F is the number of independent variables and C is the number of components in the system. For example, a basic iron-carbon system is a two-component system consisting of iron and carbon. This atomic percentage thing. To understand the phase rule, consider the example of two-component lead thin paste this diagram at constant pressure. Because pressure is held at constant value of 1 atmosphere in this diagram, it is not longer a variable. Therefore, P plus F equals C plus 1. Because it is a two-component system of lead and tin, P plus F equals 3. Finally, consider the eutectic point, or 183 degrees Celsius and 61.9% Cenk in the lead-tin diagram. At this eutectic point, there are 3 coexisting phases of a liquid phase and a mixture of 2 solid phases, one FCC for lead, the other tin with a tetragonal crystal structure. Thus, C equals 2 and P equals 3, so the allowable degrees of freedom would be F equals C minus P plus 1 equals 2 minus 3 plus 1 equals 0. 2.11 Chemical thermodynamics. The laws of thermodynamics provide the basis to describe the reactions that occur in chemical systems. For metallurgical systems, the most important thermodynamic variables are enthalpy and Gibbs free energy. The former governs the disposition of heat, and the latter governs the state of chemical equilibrium, enthalpy and heat capacity. The heat content of a material in thermodynamics is referred to as the enthalpy. H. The enthalpy represents the amount of energy in a system capable of doing mechanical work. 2.12 phase change. This liquid and solid, this liquidus line and solidus line. The formation of phases in alloys is influenced by temperature and alloy concentration. Some alloys are simple solid solutions or isomorphous over the complete range of alloying concentration. Like in the copper-nickel system, most alloys, however, do not have such simple phase systems. Lever rule. It is the liquid phase X, and this point T, this point Y, this is point Y. Equilibrium phase diagram provide a useful tool in understanding the chemical concentration of component in a given phase. For example, consider the solidification of a simple solid solution alloy like at this picture. The alloy has a composition of 50% metal A and 50% metal B. Composition of the solid phase at temperature T1 is 80% metal A and 20% metal B. Okay, the next. Composition of the liquid phase at temperature T1 at point X is the nominal alloy composition of 50% A and 50% B. Most of the alloy is liquid at T1, and so the liquid phase is nearly the nominal composition. After complete solidification, the composition point key in the solid phase is again the nominal alloy composition of 50% and 50% A and 50% B. The composition of the last remaining liquid phase just prior to complete solidification would be 25% A until 75% B at point P. Eutectic alloys and solidification. At all non-eutectic compositions, the composition of the solid and liquid phase and the amounts of solid and liquid phase at any partially solidified material may be calculated in the same way as those of the isomorphous system. The last is I want to tell about nickel. Nickel is a type of metal that plays an important role in the electronics industry, especially in nanotechnology and beyond. Nickel is used in various electronic devices such as electronic cars, cell phones, and laptops, proving its benefits in various electronic applications. Apart from that, Indonesia is also the country with the largest nickel reserves in the world. Many European countries are very dependent on our nickel natural resources. So let's protect and utilize our natural sustainability and wealth in order to increase the country's foreign exchange and at the same time develop the country. I think that's all I can explain. If there are errors in reading or symbol on and other things, please forgive me. That's all, and thank you.